Okay, so we've discussed one solution to the problem where we have more dimensions than observations. In practice, the least L2 norm solution is not necessarily a useful solution or one that we might want to use, but we've still analyzed it and discussed it because it gave us an excuse to discuss two very useful tools that are often used in machine learning. One is analysis, and the other Lagrange multipliers. So now let's discuss another type of way of doing linear regression. Let's discuss sparse L1 regression, and this is very useful and often done. Okay, so in many modern problems we have many dimensions, many features, many predictors, and only a few of these might actually be important or relevant for predicting y. And so therefore, what we're looking for when we have very high dimensional data, what we're often looking for is some form of feature selection. So we want to find the dimensions that are useful for predicting the response or the output, and just disregard the dimensions that are irrelevant. And so we believe that among our many dimensions, our high-dimensional covariate vector x, there's really only a few dimensions that are useful in predicting y, and the rest are essentially noise as far as predicting y is concerned. So least squares in ridge regression are not useful in this scenario because both of them treat all of the dimensions equally without favoring subsets. So when we want to pick subsets of dimensions, least squares in ridge regression aren't going to do that. And so we want to discuss, we're going to discuss a method now for doing regression, linear regression, where we also try to find subsets of the dimensions in x that are going to be useful for predicting y. So the way that we're going to do this is by changing our penalty function. So let's recall the general ridge regression framework where we had this sum of squared errors term, which is the sum of the square of the errors of our prediction of y with the function f of xi and w. And then we added this penalty on the squared norm of w. And so this is our penalty term, and this is, in a sense, our goodness of fit term. And for ridge regression, we use the dot product as our function. And so the general structure of this type of an optimization problem can be thought of this way, where we have the total cost that we're trying to minimize. So we're trying to minimize a total cost that we can break down into a sum of a goodness of fit term. So this is how well does our model fit the data, plus some sort of a penalty term on the model parameters. So this goodness of fit term is simply a measure of how well we can approximate something. But the penalty term then makes solutions that we don't want a priori more expensive. So first, let's look at what kind of a solution the squared norm penalty favors and discourages. So the squared norm penalty doesn't treat all values of w equally. So for example, let's imagine that we have a dimension of w. Let's consider the jth dimension of w. And we start at a certain point, and then we want to see how much do we reduce the objective function by subtracting some number delta w from that. So if we reduce the value of wj by a value delta w, then the total reduction that we get in our objective function, according to the penalty, depends on the starting point. So for example, if we have a larger value for wj and then we subtract off delta w from that, then we reduce our penalty by so much. Whereas if wj starts out at a smaller value and then we subtract off the same amount, we reduce it from wj to wj minus delta w. Starting from a smaller value, that reduction in the magnitude of W reduces our penalty term by much less. So the squared penalty on the vector W is going to first prefer to reduce the dimensions of W that have larger magnitudes before trying to reduce the dimensions that have smaller magnitudes. Okay, and so we see that the L2 norm is not necessarily going to be something that we can hope that will give us sparsity, because it's going to essentially try to make all of the values in the vector W equal in size. It's going to encourage solutions that have values that are equal in size, because when a dimension of W becomes much larger in magnitude, the squared penalty squares that magnitude, and suddenly that dimension is penalized quite a bit. Whereas if all the values are roughly equal in size, then they all contribute about the same amount to the penalty, the squared norm penalty. So our goal is to find sparse solutions. The squared norm penalty on W is not going to give us that. And so let's look first at what does it mean to find a sparse solution. So what are we looking for when we say we want to find a sparse solution? So again, our setting is that we have n data points. Each x is in Rd, and d is much greater than n, so we have many more dimensions than we have observations. And our goal is to select a small subset of the d dimensions and then switch off the rest. And so what it means to switch off a dimension is that we essentially want to make values in W equal to 0. So each entry of W, each dimension of W, in a sense, corresponds to a dimension of x. And so if the kth dimension of W is equal to 0, then when we have the dot product as our function, our prediction function, we can see that what we're going to do is we're going to take the kth dimension of x and multiply it by a weight 0. And so the kth dimension of x is not going to contribute anything to our prediction of y if we use the dot product as our function. So our goal in feature selection, in finding these dimensions of W that are not 0, is to find a vector W that first predicts well. We still want to predict the data well, but also with the added goal of having only a small number of dimensions equal to non-zero. So we want to make the dimensions, we want to make the entries of W that have non-zero values as small as possible while still predicting well. And the solution W that satisfies these is going to be called a sparse solution. So this is what sparsity is trying to do. It's trying to find dimensions of W of our regression coefficient vector that should be equal to 0 and which ones should not. Okay, so we now need to find a penalty that's going to let us do this. And we've discussed intuitively how the squared norm is not going to give us sparse solutions because it's going to penalize large values more than small values. And so once the value of a dimension in W becomes very close to 0, the penalty is very little, and so we aren't going to necessarily encourage that to go to 0 with the squared norm penalty. And so it turns out that we can achieve this sparsity by instead using a linear penalty term. So instead of using a squared penalty term, we'll use a linear penalty. Okay, so this leads us to something called the Lasso, which is short for the least absolute shrinkage and selection operator. So the Lasso takes the L2 penalty from merge regression and replaces it with an L1 penalty. So in terms of optimization, what we're trying to do is find the vector W that minimizes the sum of squared errors as before, but now we add the L1 norm of W instead of the squared L2 norm. And so by definition, the L1 norm of a vector is just the sum of the absolute values of its entries. So for L2, we had a square here. For L1, we don't have a square here. We just have the absolute value. And so this is called the Lasso. and it's also called L1 regularized regression, whereas ridge regression you could think of as L2 regularized regression. So first let's look at a comparison of these two penalties intuitively. So again, we saw that with the squared penalty, if we reduce the jth dimension by a certain amount, that the reduction in our objective, in our overall objective, as far as the penalty is concerned, is going to highly depend on where we start. So if we start from a very large value and then subtract off a certain amount, the penalty is going to view that very favorably, whereas if we start from a smaller value and subtract off that same amount, the squared penalty is going to view that much less favorably. So with the linear penalty, which is what the L1 penalty is, we simply don't care where we start. If we have a penalty that looks like this, according to the L1 minimization problem, if we start at a certain value and subtract off a certain amount, it doesn't matter whether we start from a smaller value or from a higher value. Subtracting off the same amount is going to reduce the penalty by the same amount. And so we can see already that with the L1 penalty, it's not going to favor the starting point of the magnitude. It's really going to just consider the amount that's subtracted off, which is quite different from the quadratic penalty. And so here's another way to think about it. We've motivated the problem as a high-dimensional problem, but now for visualization purposes, let's look at the problem at a problem where d is equal to 2 in this case, just for visualization, even though the intuition translates to higher dimensions. So again, we can represent the objective for the L2 problem, or ridge regression, as a combination of the least squares, a quadratic term involving the least squares solution. So this is from lecture 3. And then a penalty, which has to do with the contours. So this is for the ridge regression problem, the contours of the penalty. So again, intuitively, what does this mean? It means that all points along this curve pay the same price according to the goodness of fit term, which is, again, we can relate this term to the sum of squared errors term, as discussed in lecture 3. So every value along this curve, along this this ellipse, pays the same price according to the goodness of fit term. But if we then look at the penalty, the regularization term, we have a value that looks like this. And so according to the penalization, the penalty, this solution that pays the same price as this solution according to the goodness of fit term will pay a greater price according to the penalty. So among all the solutions that follow along this curve, we're going to pick the one that has the minimum penalty according to the squared norm of the vector w, which in this case will be this point here. So again, I can pick any three of these solutions according to these three red dots. They're all going to pay the same penalty according to the goodness of fit term, the sum of squared errors. But this point is going to be the minimum according to the L2 norm penalty on the vector w, because this is the contours of the penalty term. With L1, we have this sort of a contour. So again, we have the same exact goodness of fit term, so we have the same sum of squared errors, so this doesn't change. But now we have a penalty on the vector w that looks like this, where any point along this diamond will pay exactly the same price according to the L1 penalty. So among all of these possible solutions along this curve, the one that pays the smallest penalty according to the L1 penalty is the one that has the minimum value according to this diamond. And so we can see from this type of a intuitive plot that we're going to get sparse solutions. So if we continue to shrink our solution according to our penalty, the diamond, with the constraint that the solution must fall along this curve, we're going to eventually pick a point that's 0 along one of the axes, because we're going to hit one of the sharp points in the diamond, and those fall along the zeros of the axes. Whereas with the L2 penalty, we don't have any sharp points. We don't hit any of those sharp points, and so we don't get a sparse solution. So let's look at the coefficient profiles of the ridge regression solution versus the Lasso solution. So again, the way to think of this x-axis is as some function of the regularization parameter lambda. So as lambda goes to 0, remember that we get the least squares solution back, and so that's at this point. Whereas as lambda goes to infinity, we get as our solution a vector of zeros, because we pay an infinite price for making W have any non-zero values, and that's mapped in this way. So as this axis goes to 0, we're letting lambda go to infinity. As it goes to 8 for this specific problem, we're letting lambda go to 0. And exactly the same thing here for the Lasso solution. So this, it's not necessarily worth going into what the x-axis means, but as lambda goes to 0, we're going to 1. And then as lambda goes to infinity, again, we're going to 0. Because the infinity times the L1 penalty is going to be equal to 0 if the L1 penalty is 0 by definition. And if W has any non-zero values, then we pay an infinite price. And so we're going to pick a vector of zeros. And so our problem has 8 dimensions, to refresh your memory from previously. And so what we see is that, for example, if we pick a value of lambda such that we choose this solution, then the magnitude of our 8 dimensions is equal like this. So for example, the dimension corresponding to age is going to have a magnitude along that dimension of roughly negative 0.05, and so on. So this is the coefficient profile for the ridge regression solution. We see it's non-sparse. The only points at which a dimension is equal to 0 is at the points at which the profile crosses 0. So it's 0 by coincidence, essentially. Whereas for the Lasso, we get a coefficient profile that looks like this. So we let lambda start at 0. Notice that if lambda is 0, of course, the L1 and the L2 penalty are both 0. And so we have the least squares solution in both cases. And so these values are equal at the point where lambda is equal to 0, because the L1 and the L2 regularized regression problems converge to the same problem, the least squares problem. But now as we increase lambda for the L1 problem, what we see is that certain dimensions fall to 0 and then stay at 0. So for example, the dimension corresponding to this feature starts at this point, and then as lambda increases, it gets shrunk to 0 and then stays 0 forever. Whereas the dimension corresponding to age, again, gets shrunk to 0 and then stays 0 at a certain point forever as lambda increases to infinity. It's quite different from the L2 problem where, again, all dimensions are being shrunk to 0 as lambda increases. They're all being shrunk to 0, but they never hit 0 except either by passing through coincidentally or when lambda is infinity. And so this is the sparsity that we get from L1. At a certain value of lambda, for example, the value of lambda corresponding to this solution, we have 3 dimensions that are non-zero, and the remaining are all equal to 0.